Hello, and welcome to the North Carolina Smart Grid webinar series. We're pleased that you decided to take time out of your schedule to join us today. My name is Alex Glenn, and I work with Advanced Energy as a training consultant and instructional designer. I've worked in the energy industry for 15 years, and I'm happy to be your host and facilitator for today's webinar. As an independent nonprofit that works with most of North Carolina's electric utilities, Advanced Energy's mission is to help our state's electric utility customers get the most value out of the money that they spend for energy. To help our state's residents make well-informed decisions, we want to share information about new technologies and services when we believe that they can offer value, and we also want to share any concerns that may present risk. This webinar series is being developed using North Carolina Public Benefits Funds administered by Advanced Energy and Duke Energy, along with generous technical support from North Carolina's electric membership cooperatives, Duke Energy, and Dominion NC Power. North Carolina's electric utilities are modernizing their power generation and distribution systems. This transformation of our electric grid offers improved performance and growth opportunities for citizens, communities, and businesses. We're pleased to bring you information about smart grid technologies and systems that are being deployed in North Carolina and how you might be able to benefit from them. Today, we bring you the 5th webinar in our series, Self-Optimizing Systems. In this webinar, we will provide an overview of self-optimizing grid technologies and examples of how they're being used and implemented in North Carolina. We'd like to hear from you during this webinar. Please feel free to post your questions or comments in the Q&A box on the upper right side of the screen, and we will address your comments and answer as many questions as we can during the Q&A portion at the end of our presentation. I'd also like to mention our website, where all of the smart grid resources are available to you. We have posted case studies, educational videos, upcoming events, and links to all of our smart grid resources. So please make sure to visit ncsmartgrid.org to access this wealth of information. And please note that a recorded version of this webinar will also be made available to you. We will send a follow-up email to you where you can access the webinar recording as well as the additional links to the smart grid resources. In today's webinar, we will recap a couple of key points from our previous smart grid webinars, and we'll dig deeper into the topic of self-optimizing systems in North Carolina. We have Cece Maurer, who will provide an overview of self-optimizing systems and examples of how they're being implemented. And at the end of today's webinar, we will also be sharing a video from Duke Energy that provides a detailed explanation of how a self-healing grid system works and the devices that can help reduce power outages and shorten outage duration. We hope that you'll stay with us until the end of the webinar to watch the video. Cece Maurer is a professional energy engineer with Advanced Energy, and she's worked on our building science and engineering teams. Her current work focuses on managing the technical staff and also smart grid education initiatives. At this point, I'm going to turn it over to Cece, who will provide us an overview of these self-optimizing technologies, policies and economic factors, and the challenges and benefits of these systems in North Carolina. Cece?
Thanks, Alex, and thanks to all of you for joining us today. We will start with a basic definition of self-optimizing systems. Then we will review a few key points we covered previously in this webinar series, including challenges facing the traditional grid and technology upgrades to the current grid. We will look more in depth at self-optimizing grids and the enabling technologies. Then we will talk about a few of the policies and economic factors along with the challenges and benefits. We will define a self-optimizing grid as one that uses intelligence to automatically reconfigure the system to ensure the most efficient and reliable delivery of energy regardless of type and location of generation source. Another way to state this is that the grid automatically reacts to and mitigates failures so customers rarely experience service interruptions. The traditional grid has large central generators sending power in one direction to customers, often many miles away. The utility manages these central generation systems carefully to match the load of the customers. We are going to focus today on additional changes being made on the distribution side. Utilities across the country are investing in modernizing the grid, and the future grid will look quite different with distributed energy generation closer to customers. To understand what a self-optimizing grid is, let's look at a vision for the smart grid of the future. What you see is a grid that looks quite different from the one-way transmission and distribution system of the past. There are multiple paths to route the power, and it can flow in both directions. This type of grid requires investment in additional lines, switches, and of course sensors, processors, and communication devices. One important aspect of the smart grid is that the different components all need to work together and are interrelated. So let's take a moment to recap a few key points from our previous webinars on solar technology, AMI meters, and microgrids. Utility-scale solar has seen unprecedented growth in certain regions, in particular in North Carolina. The graph on the left shows the power output of a solar facility on a clear day, whereas the plot on the right shows a day with cloud cover and thus high variability in power output. The variable output from solar generators means the supply side of the grid can also change unpredictably, adding more challenge to matching the load. Solar can create additional need for power management for utilities, especially on the circuit it is connected to. Another topic we covered in detail was AMI meter deployment. Many utilities have invested in AMI meters at customer sites because these meters have many advantages, including remote meter reading and then also feedback on voltage, power quality, and load at each customer site. Again, for proper operation, the power grid must constantly match the supply of electricity to the load. This additional information about varying loads from AMI meters at customer sites allows utilities to operate the grid more efficiently. AMI technology allows two-way communications. So, in addition to getting information, the utility can also communicate to enable load management and real-time pricing. And then last month, we talked about microgrids. We defined microgrids as a series of interconnected loads and distributed energy generation with the ability to island or disconnect from the main utility grid. While currently microgrids are being deployed as pilot projects and at some critical sites, the utility grid of the future that has more distributed renewable energy will essentially be a series of interconnected microgrids. So renewable energy, AMI meters, and microgrids are all important components that work together. Let's take a look at them in our vision for the smart grid of the future. Our example grid has renewable energy integration on a small scale at customer sites and then also utility scale generation facilities. There is advanced metering at customer sites to help manage power quality and shift load and demand. And we see an example of a microgrid ready to island in an adverse weather event. One way of describing our smart grid is as a network of integrated microgrids that can monitor and heal itself. What we will focus on today with self-optimizing grids is how utilities are investing to upgrade the distribution system. As you can see, in this future grid, there are multiple paths to route the power. This type of grid requires investment in additional lines as currently many areas do not have this type of flexibility in the distribution to customer sites. And then there are also additional switches, sensors, and communication devices needed to route the power most effectively. These features on the distribution system form the foundation for the self-optimizing grid. There are a few elements that will be helpful to define on the distribution side. This is another way to look at the existing transmission and distribution system. Again, we are focused on the right side of the diagram. One of the elements that we'll reference today is the substation. The substation is where the voltage is reduced or stepped down from the transmission system through a transformer. The substation will have multiple distribution lines leaving to serve customers, and these are referred to as feeders or circuits. Feeders serve a combination of many customers. And along the lines, there may be additional equipment located on the poles, such as reclosers, switches, and the communications equipment. These allow disconnection or rerouting of power as needed. A recloser is a circuit breaker that can automatically close after it has been opened due to a fault. This improves reliability by automatically restoring power to the line after a momentary fault and also protects critical equipment. Depending on when the reclosers were installed, they may need to be changed out or just upgraded with additional communications. There are also other switching devices. Upgrades are being made to smart switches which can measure current, voltage, and have a processor with embedded intelligence. And then they also have a communication device to a central computer and other equipment on the grid. The upgrades that we are talking about today happen at various points on this distribution side, and they're often invisible to the customers, yet critical for reliability. Self-healing networks are one part of self-optimizing systems. Let's step through what happens in an adverse event with self-healing technology. This picture shows a typical mixed commercial and residential neighborhood. There are two substations that are powering the loads in this neighborhood. The lines served by one substation are shown in yellow, while the lines powered by the other substation are in blue. In the neighborhood, there is a fault event that happens. You can see that the electricity goes out for the customers in the upper left and middle of this territory. With the old grid, customers would have to call in to report their electricity was out, and a truck would drive around to determine the exact location of the problem. The workers may also have to manually locate switches to isolate the problem. We talked about how part of the new technology is the addition of sensors and communications. You see these sensors and communication nodes at various points on the grid in this picture. All of these communicate to locate the problem area, and they automatically figure out the best way to reroute power to as many customers as possible. The control system monitors the grid and reconfigures to restore power to most customers from the other substation. The power restoration can be done in less than a minute instead of several hours. Now, only a few customers are left without power. The intelligence helps quickly identify the exact location of the outage versus relying on customers to report an outage. Crews can be dispatched to the exact location of the problem to remedy whatever may have caused the fault event and also to restore power to the last remaining customers. I have used both the terms self-healing and self-optimizing, and I want to differentiate between these terms for today's webinar. A self-healing network uses information, sensors, controls, and communications to minimize the impact of unforeseen events. The technology used in self-healing systems includes digital smart sensors at substations and power lines, and switches to isolate a section of damaged lines. The intelligence would detect the problem and automatically figure out the best way to reroute power to as many customers as possible. Self-optimizing systems use the same technology for switching as self-healing. Self-optimizing grids are essentially enhanced self-healing networks. A self-optimizing system has many more switching devices along the circuit, allowing more segmentation and fewer customers to be affected by adverse events. Duke Energy has a 10-year goal to have 20% of its customers served by these segmented circuits and self-optimizing distribution. So with the grid of the future, instead of thinking in terms of only transmission and distribution, the utility is taking a close look at the distribution side and planning more on the design of feeders, circuits, and circuit segmentation. The functionality of the self-optimizing grid can be categorized by the features of connectivity, capacity, and control. In order to achieve connectivity, there must be multiple power flow routes for flexibility. Currently, the existing grid is set up like the picture on the left, more of a radial system from a central point, and is not designed for this flexibility. Investments are needed for additional circuits and segmentation to those circuits. The future self-optimizing grid will look more like a spider web, similar to the picture on the right. These circuits also need to be able to handle the additional potential capacity. During an adverse event, if there was not enough capacity on the second circuit to move load over, then the system would not be able to react and reconfigure automatically. Therefore, the grid needs sufficiently sized lines, substations, transformers, and other equipment to support the additional loads. This infrastructure will also help support the future development of renewable energy. And the system needs intelligent automation to optimize operations, which requires various technology upgrades in the controls, including the cellular communications network and software. Each investor-owned utility in North Carolina files a smart grid technology plan with the Utilities Commission. Duke Energy Progress is designing, installing, testing, and commissioning approximately 90 new self-healing networks and 95 new automated feeder reclosers and all the necessary communications equipment for these networks. The project is scheduled to close in early 2018. Duke Energy Carolinas has already installed 52 self-healing networks and is also upgrading its enterprise control software to be able to handle high distributed energy resource penetration. And the electric cooperatives are also employing self-healing technology. One example is Wake Electric Membership Cooperative. They have a total of 43,000 customers served by 55 feeders. About 3 years ago, they did a pilot project with Siemens Distribution Automation Controls and WiMAX Broadband on 3 high-density feeders serving 2,000 to 3,000 customers. The technology has worked reliably, and the system is automatically able to sectionalize down to the smallest outage, and they have seen faster response times for outages. They have also done a comprehensive project with voltage optimization. They are able to reduce voltage and therefore power during peak demand on all 55 feeders based on feedback data from AMI meters. We are now going to transition out of talking about the functionality and applications of self-optimizing grids and cover some policy and economic factors. Note that these factors impact the deployment of grid modernization in general and therefore also self-optimizing grids. The three aspects that I'm covering today are cost recovery, cost allocation, and asset valuation. Investor-owned electric utilities recover their capital investments through a mechanism called cost recovery. The utilities will request a rate adjustment through an electric rate case, which is heard and approved by the Utilities Commission. Many factors go into an electric rate, and these rate cases are time-intensive and expensive for both the utilities and regulators. There can be a delay between when a utility invests in generation, transmission, and distribution, and when the utility is able to request a rate increase. There are other models being explored for cost recovery, specifically for smart grid technologies in other states, such as voluntary tariffs, standby rates, or monthly rate riders. These other models may synchronize investment and cost recovery, which could facilitate grid modernization investments. Currently, costs are not allocated to reflect the true cost of electricity. Properly valuing smart grid investments would require a fresh look at the building blocks of cost allocation. Many customers pay electric rates that include a nominal charge for service and a fixed cost per kilowatt hour used. In reality, there is an enormous difference between the cost of generating and providing electricity throughout the day and year. Time of use and real-time pricing are a more accurate method to allocate costs. And then it is also challenging to value the assets for some smart grid technologies. The value of resiliency, sustainability, or security is difficult to predict, and in some cases does not fit well into the traditional methodologies used for asset valuation by utilities. According to one 2014 IEEE article, outages from all sources cost the U.S. economy between $80 and $188 billion annually. As we add more customers like data centers that operate 24 hours a day, or continue as consumers to depend on our electronic devices for basic everyday tasks, the value of resiliency increases. There are some challenges for self-optimizing networks. The primary ones are interoperability and complexity, and then also capital cost. Interoperability means the various technologies on the electric grid work together efficiently and seamlessly. In general, interoperability and communication with the smart grid is a challenge with all the different new pieces of equipment, including generation, switches, and transformers. The communications relies on software, and periodically updates have to be made. This is similar to updating our computers and cell phones periodically for compatibility. The software, firmware, and communications do add complexity to the overall grid. With self-healing technology, the benefits to customers outweigh the need to support a more complex system. And the goal with the complexity is to reduce the need to make manual adjustments. And of course, another challenge for self-healing and optimizing technology is the additional initial expense. This is why utilities must take a staged approach to investment and add technology to those lines that need upgrade the most or where the customer will benefit the most. Also, utilities such as Duke Energy are targeting to have self-optimizing grids serving a majority but not all of their customers, because the investment for all areas would not be reasonable or justifiable in their rates. There are numerous benefits to self-optimizing systems, and today we are going to focus on resiliency, reliability, and renewable energy integration. The number one focus of self-optimizing system installation is increased reliability for the customers and resiliency of the grid during adverse events. Self-healing technology provides an immediate benefit in that all the devices work together to identify and isolate the portion of the system affected by a fault and to minimize the extent of the outage by restoring power to as many customers as possible. There is a direct correlation between installing self-healing and optimizing systems and the reduction in outage time and outage costs. According to Duke Energy Carolinas, self-healing networks currently in service have resulted in over 198,000 customers saved from outages, with over 37 million minutes of outage time saved for those customers. According to Duke Energy Progress, there were over 119,000 customers saved from outages and nearly 18 million minutes of outage time saved for those customers. There are some additional benefits that may be reaped in the future, especially for renewable energy integration. The traditional electric grid was not built with renewable energy in mind as a significant resource. We could think of this as trying to put a DVD into a typewriter. It just would not work. The flexibility of connectivity and the capacity of self-optimizing systems will help facilitate the adoption of renewable energy into the electric grid of the future. Let's take a moment to review some of the key features which will help define a self-optimizing grid. First, technology is applied to enable seamless grid operation. Much of this technology is not very visible to the customer because it is mainly on the utility side of the grid. Seamless means that customers do not notice any interruptions, but it does not mean that there is not a lot going on behind the curtain. Next, there is better ability to isolate problems or faults. In order to accomplish isolation, there needs to be more automatic switches on power lines and a more interconnected grid with options on how to route power flow. The additions of sensors and communications helps the utility manage and repair the grid. The grid is able to adjust in real time to actual conditions. This means that the grid can react better to disturbances, fluctuations, and two-way power flow on distribution circuits from the substation to the meter. And last, the grid is fully controllable and flexible. And again, this means that the power system can detect changes in generation and demand and balance those needs. In many areas, to accomplish this flexibility, more circuits are being added to create a distribution network or web instead of the one-way power flow of the past. Additional segmentation added with more switches and controls allows maximum reliability and resiliency for the most customers. And at this point, I'm going to turn it back over to Alex, and we will recap and move into answering the questions that have come in during the presentation. Alex?
Excellent, and thank you so much, Cece. You certainly covered a lot of ground and helped us gain a better understanding of these self-optimizing technologies, as well as the challenges and opportunities of integrating these into the system and our electric grid. You definitely provided us with a helpful overview of the technology and also how utilities are using it to improve their operations and their services to customers. As a reminder to folks on the line, we have case studies, educational videos, and links to all of our smart grid resources on our website at ncsmartgrid.org. Also at this site, you'll find links to the previous webinars in this Smart Grid series, as well as links to the resources referenced in today's webinar, including the IEEE Smart Grid website and the Duke Energy Self-Healing Technology Brief. So please do go check out ncsmartgrid.org and access those case studies, videos, and resources. At this point, we'd like to open it up and take a few minutes to answer some of the questions and comments that have come in during the webinar. We may not have time today to answer all the questions, or we may not have an immediate answer to a question In either case, we'll do our best to follow up with you after doing some research or finding the best resource for you. So let's take a look at some of the questions that have come in. Cece, we've got a question here. Is there a concern about how self-optimizing technology performs in severe weather events? How can we help answer that?
That's a great question, Alex. The self-healing and optimizing technology actually enhances response to severe weather events. With the recent experience with Irma in September in Florida, we actually saw self-healing saved over 7 million minutes of customer interruption. And one of the benefits with self-healing and reasons that it can enhance restoration is that at winds greater than 35 miles an hour, linemen cannot work on a pole, but you can start doing the remote control with the self-healing. And so the utility is actually able to start restoration earlier before they could have sent crews out in the past. Of course, there's limitations to that. If all the utility equipment is laying on the ground, then the self-healing technology will not help restore power.
Okay, I think that makes sense. Thank you. Let's take a look here. We've got 2 more questions. This one comes in. It says, what if I am one of the customers in the 20% that are not served by self-optimizing systems? Can you help us with that?
Yeah, that's another good question. So our North Carolina utilities are looking carefully at how their system is designed and built today with the traditional grid. And they've looked at the potential segmentation and feel that this is a reasonable target. So, for example, there are parts of their territory that are very rural and maybe only served by one substation or transformer, could have 2 feeders going in opposite directions, and it's just not economical to add a substation or transformer or many miles of circuit. So for these customers, the utilities are adding just the ability to switch remotely and some segmentation. So there are benefits, just not the full self-optimizing. And the key here is for the utilities to look at how they can reasonably invest in stages, and they've not forgotten about the other 20%. The technologies like battery storage may help it be more affordable to expand self-optimizing to these remote areas.
Okay, that makes sense. And as the technologies advance and the utilities adopt those, and I'm certain that they'll work to try to reduce those percentages of people not served. So thank you for helping us understand that a little bit better. And let's take one more question here. This one, I guess, is around policy and regulation. Do you foresee any political impacts, new rules, or regulatory challenges?
Another good question. So not specifically for self-healing and self-optimizing. The regulators are pretty aware of self-healing and they see the benefit as it's been demonstrated and documented. And the same benefits really apply for self-optimizing, just moving to that next level with the additional connectivity, capacity, and control. So if the North Carolina utilities did try to reach all customers, it would not be a wise use of ratepayer money, and that might bring some challenges. But that's why the investments are targeting most customers, but not every single customer. Okay. Great, Cece, thank you. And those were certainly some very thoughtful questions. Thanks to everyone who submitted a question. At this time, we'll need to move on and wrap up with our self-healing video from Duke Energy. And we'd like to end today's webinar by sharing that video by Duke Energy.
And this video provides a detailed explanation of how a self-healing grid system works and the devices that can help reduce power outages and shorten outage duration. Now, we saved this video until the end because depending on your internet connection, you may experience some lag time or delays in viewing. If this happens, or if you have any problems watching the video, just check your inbox for an email that's coming from us that will include a link to this video, and then you can watch it at your convenience. We'll also include our satisfaction survey in that email. Please help us improve by filling out the survey that's in that email so that we can continue to make these webinars valuable for you. Folks, we're grateful that you chose to take time out of your day to join us for the webinar. We hope that you'll enjoy the video and have a great rest of your day. Thank you so much.
Every once in a while, it happens. An unforeseen incident occurs, and you lose power. But what if there were an electrical system that automatically reconfigured itself? So when an unexpected event happened, the problem was isolated and the power stayed on in most areas. At Duke Energy, we're making this kind of self-healing system a reality. We're investing in advanced technologies that are transforming the grid into a dynamic electrical system with the ability to automatically detect, isolate, and reroute power when a problem occurs. How does a self-healing system work? Let's take a look. Welcome to Orchard City, a community probably very much like yours. It's made up of residential and business customers, some with critical power needs, such as hospitals and data centers. Orchard City's data center, school, hospital, and select homes are served by the Miller Street substation. Now, let's see what happens when something causes the power to go out. Without a self-healing system, the power line damage could mean a power outage for many of these customers. A large part of the community could go dark until Duke Energy crews were able to locate the problem and make repairs. But thanks to self-healing technology, digital smart sensors at substations and on power lines detect the problem and communicate with the control system. Switches automatically isolate the damaged section of line. The control system continually monitors the state of the grid and determines the best way to reroute power to as many customers as possible. The control system automatically reconfigures the electric grid to restore power on the undamaged section of line. In our animation, we slowed this process down so you can see the series of events. In reality, this entire self-healing process typically occurs in less than a minute. Customers whose power was rerouted may have experienced the entire self-healing process as a brief power interruption rather than a full outage. Self-healing technology also improves how quickly power can be restored. Once Duke Energy line crews complete their repairs, a system operator can return the electrical system to its normal configuration with a single command, eliminating the need for manual switching. These investments in modernizing the grid bring many benefits. First, we now have more information about the state of the grid. Second, the control system continuously assesses the state of the electrical system for potential issues that could arise. And third, as you saw in Orchard City, the system can perform enhanced restoration to the grid. The system can rapidly detect and isolate problems, protecting the portion of the grid experiencing failure from the rest of the system. The result is, fewer customers experience a sustained outage during repairs, and power is restored faster. From improved reliability to faster restoration, Duke Energy is investing in self-healing technologies to better serve your needs.